Mesdames et messieurs, bonsoir. Je suis très...
Ladies and gentlemen, I'm very happy to welcome you here at the University of Geneva as the Chancellor of this university for the traditional Wright Science Symposia. The Wright Symposia have been taking place for the last 30 years at the University of Geneva. It is a fantastic gift bestowed by the Wright Foundation upon the City of Geneva and upon the Geneva University, because it's extraordinary for us to be able to greet extraordinary scientific celebrities, and it's also a tremendous opportunity to cover a wide field of subjects. We are privileged indeed because it's a 450-year-old university. Some drawback to it. You see that there's a water pipe had burst last night, so it's quite possible that a few drops of water are going to fall, but don't be too frightened, everything is under control. So if there's water falling, think of Calvin and the Bez, who had experienced even worse situations a few years ago. So the Wright Symposia is what brings us together this week. We're going to talk about the sun. It's a fascinating topic for all sorts of scientific reasons, fundamental science reasons, but also in terms of applications, just to better understand climate developments and perhaps even put this energy to use and harness this energy. So it's typical of a university like ours. We try and understand the very detailed mechanisms of nature, at the same time how we can use what we understand for the good of society as a whole. So now I'm going to give the floor to the president of the foundation, Professor Thierry Courvoisier. He's an astrophysicist, so I think he is the man to introduce the topic for this evening. And he is at the helm of this foundation, and he is going to bring science and society together, because as president of the Swiss Science Academy, he wants to spread the good word of science, and is doing a very good job. So thank you very much, Thierry, for all you have done and are doing for Swiss science, and thank you for introducing the conference speaker this evening. Thank you.
Monsieur le Recteur.
Chancellor, you have mentioned Calvin, and I have heard Calvin mentioned many times in the last 60 years. First time that I've found his name associated with water. Fantastic to greet you here in the framework of the Wright Symposium, which are very, very popular, thanks to Dudley Wright in 1980s, understood how important it was to share scientific results with the people of the city. And these symposia have been very successful thanks to the hard work of all the members of the foundation, in particular that of its president until last year, Maître Jean Patry. So we should pay a tribute to all his unstinting efforts and ceaseless work. Thank you, sir. The topics of the symposia are chosen by the scientific committee. We have with us Jean-Pierre Wolf, Yvan Rodriguez, and the representative of CERN, James Gillies, and this week we're going to talk about the sun and our relationship with the sun. The format has changed somewhat this year. First of all, there's the conference this evening, and you want to hear about science, and you want to hear people speak properly about science, but a lot of our citizens don't necessarily want to spend more than an hour in a university bench, but we all buy, we all vote, we are all called upon making decisions in our lives, and these decisions have to be based on rational thought more often than not, and they are to be based on knowledge. And therefore we thought it important not only to receive you this evening and to pass on as much as we can, but also to address ourselves to all our fellow citizens. And that is why we've decided to organize a show that is to do with one of the topics which is very close to our hearts, i.e. the sun and time. A show is on every evening on the walls of Unibastion. It's a spectacular way of acquiring a tiny bit of knowledge, and as far as we're concerned, it's a way of extending knowledge to the whole of the city, and you'll be able to see the show every evening at various times until November 23rd. In closing, I'd like to thank all those responsible for organizing the colloquium, the members of the foundation, the members of the scientific committee for their very constructive work. Thank you to the university, thank you to you, Chancellor, for very fruitful cooperation, or even juicy cooperation, if I can call it that this evening. Thank you, Professor Menet-Georges, for having organized the scientific part of this week and your unstinting efforts of the last few months. And I'd like to thank also Madame Lozano, who's in charge of organizing the whole symposium, and Mrs. Cisbane and her colleagues from the university. They've been also working very hard to make this a very successful event and to maintain a strong link with the university. We'd also like to thank all the speakers. We are honored indeed to listen to what they have to say. I wish you an excellent week, and I shall now give the floor to Professor Georges Menet.
Cher Thierry, Monsieur le Président.
Thierry, members of the Wright Foundation, Chancellor, welcome to all for the start of the Wright Symposia. Before I say a few words, a few practical announcements. You've received a form on which you can write your questions. They will be picked up at the end of the conference. The end of the presentation, we'll have a quick break after the presentation. Those who want to leave can leave, and those who want to entertain questions may remain, and we should close the proceedings at 9:15. Now, this is going to be held in French. Those who want to listen in English, I imagine you've got your headphones on, and the other three speakers will speak in English, and you'll have to hang on to your earphones if you want to listen to the presentations in French. Then there's the show. It's been organized for all the children, whether they are aged between 7 and 77 years. And there are the 4 presentations, 4 conferences to learn, to be surprised, and to whet your curiosity this year. We're going to talk about the sun, its surprising aspects, and its links with Mother Earth. Tomorrow, Mark MacDonald is going to take you to the center of the sun. And then Thursday, Jerry Meal is going to tell you about recent information as to solar cycles and global warming. And finally, Friday, Daniel Nocera, who's going to arrive on Wednesday, will explain how to use solar energy as plants and leaves do. This evening, we are going to listen to a presentation entitled We, the Children of the Stars, explaining the links with the star of the day that has warmed us since time immemorial. I have the great pleasure of welcoming a real maverick, André Braich. Is he in the room? Yes, is he there? Well, that's already something. He's a passionate researcher, and a very interesting one at that. He is professor at the University Paris Diderot and at the Space Agency in Saclay. At the end of the 60s, he studied supernovae, the phenomena of chaos physics, dynamics and flattening of galaxies. He then decided to specialize in the solar system. He has become one of the world specialists of the dynamics and the developments of planetary rings, as well as the formation of the solar system. There's a lovely sentence that I'd like to quote. There's very little matter in the rings, and André Braich says that the rings are a bit like a scent. very little matter and so much emotion. In 1984, he discovered the Neptune arcs. He gave them names: courage, freedom, equality, and fraternity. He's a member of the space probe Voyager program, 79 to 89, since 1990. He's the French member of the imagery Cassini program, which is exploring the world of Saturn until 2017. He was one of the 6 members of the international committee in charge of defining the word planet, definition which was adopted in August 2006 by the International Astronomy Union. He's published more than 200 articles and books. He was awarded the Carl Sagan Prize of the American Society of Astronomy in 2000 and the prize Jean Perrin of the French Society of Physics in 2006. And an asteroid has been named after him, 3488, and he is now listed in a French dictionary since 2009. Obviously, he's a very creative speaker, but I'd also like to say that he likes to promote the word Homo regulus rather than Homo tristus, and I'm sure that tonight he's going to give us the taste for Homo regulus, because he really makes science fun. We're ready to listen to what you have to say. Thank you.
Bonjour. Je suis comme au commissariat.
I have the feeling I'm at the police station. I know nothing, but I'll tell you anything you want. If you could dim the lights, please. Oh, God. Well, thank you very much for all these very kind words, but now it makes very difficult, because if you've been told that it was a very bad speaker, it would have been fine, but if we're told it's a good speaker, then obviously you can only be disappointed. Now, there's another thing. I realise that we've only got about an hour, and this is a problem, because I'm unable of making a presentation that lasts less than 3 hours, so it's a problem. So I hope that the chair will interrupt me brutally when I go overboard. One day I was supposed to make a presentation in the evening in Paris at 9 o'clock. I arrived late, 9:30. People were waiting for me. I felt guilty. I wanted to be kind. So I started to speak very rapidly, and then suddenly I was a bit tired. So I said, "Do you mind if I drink a glass of water?" They started laughing. And when I looked at my watch, it was 3 o'clock in the morning. So I said, "We'll leave it at that." They said, No, we've got questions for you. So put your questions. And they let me go at 6 o'clock, so I went back home. It was 7 o'clock, and my wife opened one eye and said, "Where have you come from?" "I've just done a presentation." She said, "Pull the other one, it's got bells on." So today, I know that they switched off the water in the hotel room, and I can have a shower here. It'll wake me up. So, the sun, how did it all start? I will come up with a menu card, and you'll tell me what you want to eat. So I'll start off with an introduction, which is going to take some time, unfortunately, but these are presentations for the whole city. So I'd like to say, what's science for? Why are we doing science? Why governments give us money to do money? Why am I paid an astronomical salary every month by the French government? What's it for? What's the purpose? You see that there is a reason for it, and if you've come along, it's because you're interested in science. I'd like you to disseminate this good word, because I'm sure with these homo tristus that keep on talking about bad things in life, we need to develop further and do more science than the past. Then, let's start with the origins of life, of Earth, of Sun, the universe. For those who want to leave, well, we don't know where all this has come from, but that's the short answer. But it's very difficult to answer this question, because if I ask you and tell you about the origins of the Earth hasn't started off from nothing. What's the origins of the Earth, of the Sun? When we talk about the origins, we don't talk about the beginning of a story, but the end of our story. So if I ask you where you come from, each and every one of you will tell me that it's this result of a love story between your mother and your father. And if you want to create the Earth, well, we're going to explain what has happened around the Earth, how the universe came about. And when we talk about the Big Bang, you've heard about the Big Bang. It's not the start of the universe, but we astronomers, we can tell you what's been happening for the last 150 billion years and what happened beforehand. If there is a before, let's leave it up to the next man, because he needs to be able to find work. So the philosophers' debate has been lasting for thousands of years as to the creativity we've created the world. You cannot create something from nothing. And others say eternity. World has never been created. There's no beginning, no end. It changes all the time. As Pierre Dac said, eternity takes a long time, especially when you've come to the end of your life. So we've achieved extraordinary progress in the last few years, because for the first time in millennia, scientists and astronomers have agreed as to the general lines as to how the sun and the solar system came about. We are not quite in agreement as to a number of details, but we tend to agree on major aspects. I'm moving around because I'm trying to get away from the light. So we'll start off with the origins, and if we have a little bit more time, I'll talk about the recent developments as to the formation of stars and the formation of disks that I'll be able to mention very quickly. In any case, it'll be 3 o'clock in the morning, and the president will try to pull me away from the stage. So I have about 40,000 slides, but we'll start with the first one. Let's start with the rings of Saturn. Why the rings of Saturn? Because it's typical. A child at school will immediately know what it's about. If you are asked to paint a sky, you paint the sun, and this gives you a third dimension. It's a beautiful object, and it's something that we don't really understand. Some who've succeeded, like Galileo, Laplace, Maxwell, Poincaré, the mathematician, not the Prime Minister, Henri Poincaré. So try and study the rings without understanding how it was coming about. So we tried to understand what was happening around the rings, and we as astronomers, we are not as fortunate as chemists and physicists who work in their labs. Chemists can take objects, heat them, and then you write down laws, and then students that learn it by heart, and that Bob's your uncle. As far as astronomers are concerned, we cannot cut the sun in two, and we can only observe using our 5 senses that usually allow us to understand the world: the taste, smell, touch. We can only look at these things, and you can only look at it from one angle. From Saturn, the Earth is close to the Sun. If you set off a space probe, you can look at it around the planet like a pointer to understand what is happening. This is what we're going to do with Saturn. We'll look at Saturn against the light. It's a bit like looking at your favorite lady. You've got the silhouette, and against the light you don't see any details. So this is what it looks like, Saturn against the light. You see there's a lot of dust particles around it, and you've got the rings. And it's very difficult to take a photo like this one, because the space probe Cassini here, if you open up the ends, you have to close it, open it when the sun is there, and then close it again. And we're 5 billion kilometers away from the Earth, and it's not easy to communicate, so it's a bit difficult. We've taken the photo. You see the arrow, and you can see a little dot. It's a satellite? Not at all, it's the Earth. And the day we took the photo, Geneva was on the right side, and it was sunny. So you're on the photo. So to celebrate this evening, I wanted to take a group photo. So you're there. So when the policeman asked me to show my papers, I show them this, and I'm there with all my friends. So when I show you this picture, it's not just to show you a pretty picture, just to explain that the Earth and Saturn, Earth and astronomy is the same problem, because we wonder whether there's going to be global warming. What about pollution? Is that going to upset us? So what's the future going to look like? If we really want to answer that question, we should, like the physicist in the lab, carry out experiments, cut the Earth in half and heat it up. It's not necessary, because you just have to wander from one planet to the next. You'll see some warmer ones, colder ones, and you can understand immediately their effect on temperature, density, composition, etc. So if you look at Saturn, you will be able to understand Earth better. It's the same applies in life. When you have a problem, you mustn't look at it straight before you. You have to take a step back and try and understand it from afar. And that's what we understood with the Earth. We've seen cyclones in the pole, North Pole and South Pole, 600 miles an hour. But people who look at this weather phenomena, if they've been able to test their model in extreme conditions, like industrialist is going to test its products. So this is how we improve our knowledge on these objects. So if I had been invited to Geneva in 1840, I was already there. And in 1840, Auguste Comte made presentations and taught physics in Paris. He said, we'll never find out what's within the sun. We'll find out tomorrow evening because we'll never be able to go there. And he used to say, astronomy is for men, so I suggest that women read books written by men. And I just asked my students to tell me what's wrong with those two sentences. So Auguste Comte, of course, you can't go to the sun, but you will see that there are particles, neutrinos, that come directly from the sun. And even in Auguste Comte, there were equations. When they are written, you can find out the temperature conditions within the sun. So he's a fantastic philosopher, but a very bad mathematician. So what's the solar system all about? This is just a drawing to explain that you have the sun and there are 8 planets, not 9 planets, 8 planets. There are 8 planets. If you put a question, the very interesting one, Jupiter, Saturn, Uranus and Neptune, because they're made up of hydrogen and helium like the rest of the universe, because they have all sorts of satellites, lots and lots of satellites, because they've got rings, Jupiter, Saturn, Uranus, Neptune. And close to the sun, bit of bits and bobs. We're on the 3rd bit. There are no satellites, there's no hydrogen, no helium, and no rings. For a very simple reason is that the universe is made up of hydrogen and helium, which are the most simple atoms. And when this is created, it's very hot, and these are agitated and try and escape. So far from the sun, there's hydrogen and helium, and you can come up with bigger planets. This evening you want to prepare a soup, so you put water, a bit of salt and pepper, and the phone rings. Best friend is spend 90 minutes, all the water is evaporated, you only have a bit of salt and pepper. The same happened to the Earth. That's what happened to the Earth. So what you have to understand is that the Earth, unlike what we thought in the 19th and the 20th, is not an isolated object in the universe. It's constantly subject to conditions of the outside world. It's bombarded by meteorites constantly. Thousands of tons fall every day, but there are deserts and oceans. It's bombarded by the sun. There are charged particles that hit the Earth, but there's a magnetic field that protects us. It's influenced by Jupiter and Saturn, the rotation axis. If they didn't have, the moon would have to oscillate from one to the other, which would be a problem. It's a bit like a tightrope walker. If you take away his pole, he will fall immediately. So you'll find out Thursday evening why the activity of the sun can affect the Earth, and why it affected the Earth millions of years ago, and why the gravity can change the angle of the axis. We are constantly influenced by the outside. It's a bit like the history, like the story of the world. A few centuries ago, we only talked about Europe and China, and the navigators discovered Australia, America, and now the Earth is a whole. And Christopher Columbus did have an impact on our history, and the same applies to the solar system. What we discover is going to affect the history in the millennia that are going to follow. So there are books that you can read if you're interested in what I'm saying. And I'd just like to comment a few of the points. I spend my time on Saturn and then I come back to Earth. I pick up a newspaper, look at television, and I say, oh, my goodness, it's terrible. I don't understand, because 2014 is far better than 1114. We're living in a world where we've never lived so long. We've never been looked after so well. Boat landed in Bordeaux. There was an epidemic. Everybody died. If everybody lost their crops, then everybody died of hunger. If you travel from Paris to Marseille, you were attacked 8 times on the stagecoach. If you go to Marseille today, you will be attacked less than 8 times, I can assure you. So a lot of progress, and then we're told that there's a crisis that's ongoing. So whatever year you were born, I mean, obviously I would prefer to be born now than 6,000 years ago. So, you know, if you smile, the world smiles with you, and if you cry, nobody will look at you. So I am part of the first generations that hasn't been involved in a war. So I'm very happy to be living in the world that I live in. I'm terribly sorry for those who will know this off by heart. What's science for? What's the purpose? Well, I give you an example. To walk, you need 2 legs. If somebody said we're going to save a bit, we'll cut off a leg and your trousers will cost less to make. Well, you obviously won't be able to walk as well. So what you need your 2 legs for: fundamental science and applied research. And fundamental research. Applied research is for our own comfort of life, and a few consequences. In the 19th century, we did away with slavery, not because we were being altruistic or generous, or because we were kind, but simply because we invented electricity. We didn't leave slaves any longer. So that's the advantage of science, and that's the whole history that is based on the advance of science. And I won't talk about applied research. I'm only going to talk about fundamental research. What's the purpose of fundamental research? The purpose of fundamental research is to understand the world. That's the only purpose, to understand the world. No idea, no application whatsoever. And all fundamental discoveries have found an application. Take a cell phone. Without quantum mechanics, it doesn't work. And without global positioning system and mechanics, it's never going to work. So I'm very sad, because everybody tells you, I'm in the train, and they're on their cell phone. Where are you? I'm on the train. So it's a bore. It's a real bore for those who are sitting next to them. So to understand what do we use, it's a bit complicated, but I understand, so I can find my way around. The brain, is it the most adapted tool? What's the brain all about? It's the result of evolution, so that we can survive. But there are 3 functions: escape from predators, to eat, and to reproduce. When I see a tiger, I try and run a mile. If I see a lady, I run after the lady. And is this tool the best possible object to understand the world? Not necessarily. So let's take a rhinoceros, a giraffe, a hippopotamus, or a monkey, a cat, a dog. These animals share with us 90 and 99% of our genetic code. It's the same. And we have 1% more, and we understand everything, and they would suppose not to understand anything. I'm sure that my dog didn't understand Einstein's theory of relativity. So are we capable of understanding the world? The answer is very simple. Well, I don't know. And as I don't know, I'm going to try. We've been trying for the last 4,000 years, and we are getting results, so we're going to go on.
And immediately you find doubt and humility, which are qualities that are not shared by everybody, including politicians. So science means humanism, curiosity, liberty, tolerance, etc. What's the difference between someone who is a humanist, etc., and someone who is not? In science, you can always refute the hypothesis. If you want to prove me wrong, then you can discuss it with me, and this is a scientific approach. If you cannot refute my thesis, this is not a scientific approach. I put here a car here on to remind myself of what I wanted to tell you. Take the example of a car. If I tell you cars are persuaded, are convinced that trains have been built for them to be distracted, nobody can prove me wrong. This is not a scientific sentence. However, if I tell you all cars are black, you just find one white car and you disprove my theory. This is a scientific sentence. Everything scientific can be refuted, contested, discussed, and proven. That is the scientific approach. Science is constantly going from observing the world or experimenting, if you're a chemist or a physicist, and trying to find a theory to explain that. Explaining or coming up with a theory without proving anything is, of course, extremely dangerous. The major massacres in humanity, in Siberia, in everywhere else, is the proof, is the result of this. Science, however, constantly advances by going from observation to theory and vice versa. A scientist can never tell you what is true, but can always tell you what is wrong. In the middle of Jesus land, as it's called in the United States, some people claim that the Earth has been in existence for 6,000 years, but I can tell you that it is wrong. Now, what is the use of science? Science is entirely linked with progress. There is a very dangerous current of thought trying to disconnect science from progress. Because science is something to help us doing away with violence. Take the example of two people talking, even if they quarrel. At the end of it, someone has no argument left and suddenly hits the other. If you have no further argument, you hit the other. This is the reason why I'm talking for so long. I don't want to be hit. Now, our colleagues, one of our colleagues, Claude Allègre in France, told me, you know, there is a lot of violence in schools, and I told him, well, of course, because children are full of energy and our school programs are boring, so they want to get away with their energy, and we should teach them astronomy. And he took me to difficult quarters in Marseille and other places with drugs and all sorts of things. And then I gave them a conference, not such a long one as this one, of course, but I saw in my audience people started to feel interested, with the exception of 5 to 10%. But all the rest of them were interested because they suddenly discovered things that they didn't know about. Of course, you can always send the police or the army, but one day, on a different evening, I was talking with Jacques Chirac, and I told him, when you have difficulties, send astronomers first and then the police afterwards. I think science and culture is extremely important. It's something to fight against obscurantism, the religious dark side, but also, let's not forget that in the 21st century, printed papers still print your horoscope. Can you imagine? Don't buy them, please. Even here, I'm not going to talk about nuclear power plants, but the word nuclear, for example, is being bandied about for all sorts of good and wrong reasons. Because many people are against nuclear energy, but whatever you do with energy comes from the sun and is a form of nuclear energy. In other words, these people simply don't know anything about the rules and the laws of physics. I replaced in the speech of someone the one word by the word water. And you can give a whole speech saying that water is extremely dangerous, you can drown in it, so cancel and suppress all water on the surface of the earth. Of course, without water, you wouldn't be there. If there is no water, you die. But if there's too much water, of course, you die as well. In other words, all these examples show that many people are lacking a lot of culture. Science is also good against unemployment, because if you want to fight against unemployment, you have to discover and to practice science. And some countries do that better than others. Rabelais said that science without conscience is the ruin of the soul. Very often you dissociate literary teaching from scientific teaching. And unfortunately, some people cannot combine both types of knowledge. What I claim is that culture is everything at the same time. It's painting, it's music, it's culture, but it also is science and scientific knowledge, because science is a way of understanding the world. I think that if I take the example of a hammer and of a rocket, with a hammer you can build a house, but you can also kill your neighbor. The hammer is not responsible for your neighbor being killed. Same thing for the rocket. Science is neither good nor bad. It is. It simply is. And what counts is the way you use it. So we have still a lot of work to do. We are living in a world where people who know nothing about anything are misusing figures. And at school, I don't know how it is in Switzerland, but in France, in any case, you tend to ask school children to repeat what the schoolmaster said. It would be more important to have them think by themselves. This is a good image of the organization of research in Europe, I think. Bureaucracy, red tape has invaded us. In France, in any case, and in Europe in general, researchers simply produce paper. 60% of them write forms or fill in forms to get credits, and all the others read them. Whenever you publish, people count the number of articles you've been publishing, not the number of errors that are in these papers. Now, this should be worth another topic and another conference. In any case, in the south of France, when you sell your car, you clap in the seller's hand. I refuse from now on to sign any paper that I haven't written myself. Now, let's come back to science. This is a typical image of our era. For the first time in the history of mankind, man goes out of its cradle. One of our colleagues went in holidays not too far away from the Earth and took that picture. And that raises quite a few questions. What is time? What is life? What is matter? What is space? All these words are being used every day, even by school children. But ask me to define all these words and I couldn't tell you. What is time? Is it what's elapsing when nothing happens? There is also the biological time, the time of clocks. So let's not deal with time. What is space? Space does not exist. We are not in a universe where there is a an upper part, a lower part, left or right. What we call space is an environment with matter. So space doesn't exist. What is matter? In Geneva, you have the LHC with particles that are crossing the frontier between France and Switzerland, and that helped you discover the Higgs boson. Of course, there are always rivalries between astrophysics and particle physics, but they have the standard model. As an astronomer, I find this model a bit complicated. I tell the particle physicists that we used to have the Ptolemaic model for 1,500 years. And one of my predecessors in Paris was called Jean du Sacré-Bois. He was a professor in 1200, and he told students that there were 60 epicycles intricated in one another. This was wrong, of course, but if they wanted to know exactly where Jupiter was on the 14th of December 1345, they would get the answer. So this model was not totally wrong in the end. Now, we don't know exactly what matter is, but what is life? If you take ice crystals, if you put them into a cold environment, they would develop, but they wouldn't be living nevertheless. We are thinking about new planets around other stars, maybe with other forms of life. And this will probably be the great adventure of the 21st century. And maybe we will be able to understand better what life on Earth means. There were three major steps in our history and historical evolution. The antiquity. At the time when people used to think there is a god for cyclones, there is a god for rain, and there is a god for wind. And then other people tried to understand, the Sumerian or the Egyptians tried to develop rational thought. This is an excellent example of this mixture with the oracle in Delphi and the sun rising every morning at 6 o'clock with the trajectory of the sun, therefore. At the bottom of the picture you see the oracle telling you exactly the answer to your questions, and the answer very often was there used to be young ladies welcoming the crowd in white robes and telling them something incomprehensible. Now the other way was is depicted here on the upper part of this picture with the observation of the movement of the sun. The single problem was that the Greeks neglected a bit observation. Then there is a second time. On the 17th February of 1600, Giordano Bruno was burnt because he said that there were stars around the sun and maybe forms of life, and he was considered a heretic. He also said that Mary was not a virgin, and that didn't that wasn't liked. In any case, he was burnt. I wouldn't have done so, but that's life. And then a few years later, 1610, Galileo came. Throughout the Middle Ages, we used to have techniques for polishing lenses, and when people grow older, they see less well. And there were craftsmen who used to polish lenses and to produce glasses that rich older people could buy. 10 years later, some people said, but if you put two lenses next to each other, you can buy a kind of telescope or a microscope, see what is extremely far away from you or something that is very tiny. So to start with, the lenses or telescopes were used to try and see what was happening on the other hill with the warring partners. And then Galileo said, let's see what's happening in the sky. He found craters on the moon and many more stars than were thought of, and particularly 4 satellites around Jupiter. But the dogma at the time was that there was the Earth at the middle of the universe, and things would evolve around the Earth. Now, Galileo proved that that was wrong, and one of my colleagues gave me a facsimile of a manuscript that was written by Jesuits in Latin at this time, and they made a remark in Italian saying that this is a very sensitive political issue. Just a mention of 2 colleagues who said, first of all, Erasmus, who said homo fit non nascitur. This is one of the reasons why I became a scientist. This means you do not become, you are not born a man, you become a human being. Therefore, this is essential. And then you have Fontenelle, who lived about 100 years at the time of Louis XIV. It was very rare, at a time also where women were neglected. He defined science in the best possible way to my mind. He said, it's curious mind and bad eyes. And he was quite a character, actually. When he was 90 and he saw a nice, good-looking woman, he said, if only I was only 80. Now, my question is, what should we observe and how should we interpret it? If someone from the outer space came to the Earth and saw us, what would they observe? What would they interpret? What is interesting here? The mask, the body, the skeleton. Now, the mask, for example, gives you one piece of information. In Greek tragedy, when the actor came in with a mask on their face, everybody would understand what it meant. This is Audrey, the skeleton of a friend of mine. She's also very good looking. Now, if you look at one aspect, you have not necessarily understood everything. It's a bit late, and to avoid you to sleep in, I shall drop in a few jokes. You know the story of two pygmies who are blind. They live in Africa and they want to know the world. So they are trying to find a way outside of Africa and then find an elephant. One of the pygmies touches one part of the elephant and comes back to their own village and explains what they've touched. And of course, nobody describes a whole elephant. You also know the story of a maverick researcher. He asked for a...
Il coupe une patte de la puce, il est fou, hein. Il coupe une patte de la puce. Saute, elle saute.
A flea, it takes a flea and cuts one leg after another. And at the end, the researcher says that the ears, which were used to obey the command, please jump, are located at the end of their legs. In the 40s, when I was younger, people were heated with coal. And I noticed that if you put your hands on the coal, you could paint the walls of the house. My mother didn't like it very much. And then, when we heated ourselves, coal became red. And of course, I didn't put my hands on them. This is called natural selection, if you put your hands on them. Now, you notice that colors make all the difference sometimes. And you have fundamental colors, like the colors of light. Galileo went on a hill next to Florence and made all sorts of experiments with his assistants. But Romer, in 1676 in Paris, noticed that the Earth was closer or further away from Jupiter with differences in time. And he calculated that the speed of the Earth was 230,000 kilometers per second. At the time, Louis XIV told his minister Colbert, please develop science and art. Take the best ones in Europe, ask them what they want to charge, and pay them 3 times more. This is not exactly the way we do it nowadays, but nevertheless. This approach is fundamental. The further you look into the universe, the further away in time you also are. Time and space are linked together. Maybe you remember 2 years ago when CERN produced protons and they went in front of a wall. They were sent to the neutrino in Gran Sasso in Italy, and the story went that they were faster than the light. At 8 o'clock in the morning, everybody said, this is a major discovery. At 10 o'clock in the morning, people said, there might be a problem. At 2 o'clock in the afternoon, people said, I'm not here to answer any questions. So I wrote an article in a paper. I wasn't very kind because I said that it was not light that was faster than everything else, but information that was faster, or too fast, actually. To top it all, the answer or the explanation to this anecdote was that there was something that had been welded not well enough. Nevertheless, a minister went to the press in the morning to tell the whole public that it was a major discovery. But of course, there was nothing new in the fact that neutrinos would go throughout the whole Earth. This was a communique that was totally ridiculous. Even a minister for research was someone who absolutely had no idea about what she was talking about. She had been recruited on the basis of other criteria, I think. Well, in any case, what is most important in all this story is evolution. This is Geneva in 250 million years. Geneva will be further from the polar circle. If you want to buy a house here, don't forget telling the new owner that conditions, weather conditions might change in the next million years. In other words, Geneva will be further than the polar circle. But in 1 billion years, what will happen? We will be at the center of the sun. In the sun, 4 atom hydrogen build up 1 helium atom. Therefore, there will be a higher density, higher pressure, higher temperature, and with time, the sun will become warmer than at the time when life appeared. At the time of the appearance of life, apparition of life, it was about 30 degrees cooler than it was now, and now in 1 billion years, there will be no life on Earth. Don't be too sad about this. Life will be over in 1 billion years, but we'll still have time to think about a moving company that might help us to find another quite nice place to live in the universe. So this is the evolution of Geneva. This is Geneva now, Geneva in 200 million years, and Geneva in 1 billion years. But I'm not sure about the jet d'eau. Don't be sad about this. Sun will have a wonderful nebulosity, just like in certain countries in Africa and Asia, when there is death in a family, people dance and shout, and this will be the case with the sun, but in many, many billion years. Major progress in astronomy have been the following ones. We will have a better knowledge of atmosphere. The atmosphere is there to protect us from gamma and X rays that would otherwise kill us. Thanks to the atmosphere, we are able to breathe, but it also prevents us from getting information. This information veil is now cut. We are now in a position to see through and to see exactly what are these gamma rays and all the other wavelengths that our ancestors didn't know about. We can also walk or travel from one planet to another and discover new worlds. This is the major discovery of our 21st century. When Van Gogh used to paint a sky in Arles, he was in good health. And then he became mad and he was put in an asylum. But he went on painting. And what did he paint? This. Of course, it's the painting of a madman. But this painting is much closer to reality. If your eyes were able to see all the rays, you would see the gamma rays, and you'd be constantly dancing and frolicking. This is exactly the real presentation of the heaven. Now, whatever you're doing here, all these rays that you can find depicted here exist on Earth. This is the map of the sky with Orion here, the Milky Way, Sagittarius here. You know the heaven, of course, and you know the map. This sky is different according to the wavelength you look at it with. My image is that if tomorrow, for example, you go to the opera or to the concert with 150 musicians and you hear only one instrument, the triangle, for example, if you can only hear the triangle, this will be a boring concert for you. But this is exactly the simile with what we used to know about astronomy. Astronomers nowadays can hear the whole orchestra, and it changed their lives. This is a depiction by Granville in 1850. The dream of exploring new planets. This dream is becoming reality. The way we travel to these planets is, of course, slightly different. As a member of the government, I was able to take part in the Voyager program. We explored Jupiter, Saturn, Uranus and Neptune. This is the first photography of the Earth and the Moon with Triton here. This is absolutely extraordinary. This is Io, a satellite which I was in charge of counting the number of craters. You can count craters and know exactly the age of the surface. When we saw this, we didn't understand anything. We thought we would see something just like the moon. And we saw this. We wondered, is this a sexually transmittable disease? What is it exactly? In black, you see volcanoes. We discovered 8 volcanoes. In the meantime, we know that there are over 110. There are many, many volcanoes. And then we launched into the Cassini probe program. With a few colleagues, I took part in a meeting in Pasadena in June 1980. Of course, ladies were not born yet. And on that day, we wondered whether we shouldn't go to Saturn. And some of my colleagues told me, don't dream, André, this is too expensive, this is too complicated, we won't make it. But my motto is, just say once that something is impossible and suddenly it becomes possible. And the mission was supposed to cost 4 billion euros. That was not much of money. I know a few bankers who are able to spend the money and get nothing for it. Now, we decided to launch into this program. We selected the scientists between 1990 and 1991. I was amongst them. Until 1997, the probe was built. The probe went to Saturn in 2004. The mission was supposed to end in 2008. But unfortunately, in Europe, people are not well paid, but for life. In the United States, they are well paid, but not for a long time. So for the Europeans, going on with the mission was not a problem, but for the United States it was more of a problem. And therefore it was decided to go on until 2010. And in 2010 people would say, oh, there would be many other things to discover. So we decided to go until 2017. I'm paid until 2019. So if you want to go on with it, I'm your man.
Saturne.
So to explore the world is to know about Saturn, the satellites, the rings. I'm not going to tell you the whole story. I'd just like to give you one piece of information which is extraordinary, which is to do with the research on life. A small satellite is Saturn slide. You see the rings, and I taught my students that the smaller the body, the deader it is. The moon is very small, it's dead. The earth is bigger and it's alive. So we expected to see a dead body. When you come closer, you see there are very few craters. We expected to have a cold pole, and we found exactly the opposite. And this was a discovery in 2006, and there are eruptions. Are they volcanoes, geysers? We spent 4 years working on it with students, and we discovered that in the South Pole There are geysers, and the model that we use to understand that there's an ocean of liquid water, slightly salty, below the South Pole. It's the Perrier Ocean, because there are lots of bubbles. It comes out the ice flow at 200 degrees, so there's a lot of water steam. At less than 200 degrees, it's like a cork. So it comes out the other side. So you've got valleys, V-shaped valleys, which have plugged the other holes. So you understand all sorts of phenomena which have taken place in 1970s, 1990s. This is explained by this. And these explosions took place in 2010, 2012, and go on. So it's a quite extraordinary phenomenon, and to understand what it's all about. Along these faults, you see 110 eruptions that have taken place since 2006, 2014, and what you have to understand, there are three things that exist. First of all, energy. You need energy, water, solvent, and carbon chemistry, which is quite extraordinary. Lots of hydrocarbons. If Bush had found out about it, he would have gone off like a shot. So if you ask me what are the conditions that are required for life to exist somewhere, you need energy, you need water, and you need carbon physics and chemistry. So I'm not explaining that there are dolphins and whales, but I'm saying that the conditions that life exists are there, so we don't know what's there. We're going to go back. And either we find life, and that would be extraordinary, quite unexpected, away from the sun, couldn't have really imagined that it could happen, or we don't find life. And if we don't find life, this would mean that the conditions are there, and nevertheless something hasn't started, so there's a missing link somewhere. And this phenomenon that we have seen on a slab also exists on Europe, on Ganymede, Callisto, Titan, and Triton. On all these satellites, subterranean oceans, the right temperature, so you should see eruptions like this one on the surface. So the other day I was in Versailles, and Louis XIV had created waterworks, and I sent it to my American friends saying, you see, Louis XIV had understood what it was all about. Here's a picture of the Voyager. We expected to see a surface like that of the moon, and it's quite extraordinary. Look at the X shape. So XY, so we have the sex of the object, and you see these black slimes. We see this vertical line and the horizontal line and a parallel. It's a geyser, and at the top you have a cloud, and you have the shadow of the cloud on the ground, so it's 20 meters high. I've seen one before in Iceland, but over there it's 8 kilometers high. It's the mothership of all geysers. And on an object like Titan, you have Venus, the Earth, Mars, and Titan is the size of Mars. I say Mars, a bit like somebody who's the runt of the family, so it's the runt of the planets. And there's lots of methane on Earth, and methane due to the cows that are digesting. So we need to understand the atmosphere is opaque, and we find a sort of shadow, and we compare what we see on our various cameras. We see a lake. It's made up of black lakes with blue borders on a brown earth. So minus 200 degrees, it's not water, no, it's methane and liquid ethane. And it evaporates in clouds and then rivers, and you have the same cycle of methane as like the cycle of water. And below there are subterranean oceans. And at minus 200 degrees, the water ice is harder than rocks. So it's quite an extraordinary place. I've practically come to the end of my introduction. We'll be able to get down to the most important part of my presentation, our origins. Look at this part of the sky. It's a bit like if you stick out your arm with a needle, and it's about as big as the tip of the needle. And in this bit here, there are lots and lots of things. There are galaxies, the stars, the whole communities of stars. And a galaxy is to the astronomer what the molecule is to the physicist. So it's a whole of galaxies where you have thousands and thousands of billions of stars and lots and lots and lots of them. So 4 people helped us understand what was going on: Albert Einstein, Hubble, Georges Lemaitre, and Georges Lamothe. Einstein wrote a theory, that of relativity, to explain all the physical laws. Edwin Hubble realizes the further the galaxy, the more it travels away from us. And if the world is expanding, and if we go back a bit, it should have been as small as a pea. It must have started off with something. Gamow, I love Gamow. He had a lot of humor. And I like Democritus and Gamow. He made a joke. If everything was grouped together, if everything was amalgamated and there was a lot of radiation, perhaps all the atoms were manufactured at the same time. And he wrote an article, a joke. He signed with Alpha. Beta was a Nobel Prize laureate, so Alpha, Beta, Gamma. So you see, in this article, which was very funny indeed, at the beginning, if there was a lot of radiation, perhaps something has remained, a bit like in this amphitheatre where I've stopped the water for running. If somebody runs in with gas at 3,000 degrees and then leaves the room, take the thermometer, and then you check what it looks like 1 day later, 1 week later, there's always something that remains. And he wrote an article in the 1940s, I can't remember exactly when. Not a lot of people paid attention. And a couple of years later, 2 young people who worked for Bell, they were building an antenna, an aerial, and to communicate with satellites. And they realized that there was parasites, and they asked the army, stop doing what you're doing. Oh, it must be radio. Oh, stop the radio. And then they thought, it's pigeon guano. So they cleaned the aerial, and there was always a lot of parasites. And at the end of the day, they wrote a whole page article called How to Do Away with the Parasites of Radio Aerials. And perhaps it's Gamow's theory. And that's how they were awarded the Nobel Prize. They found the fossil radiation of this stage at the beginning of expansion. And this Aisha picture, there's not a center of expansion. You have this infinite structure made up of metallic infrastructure. Yes, I've come to the end of my introduction. So if you heat all this up, it's going to dilate. And every link is going to move away from the others. So everybody thinks that they're the center. The universe is made up of filaments, so it looks like a sponge, and this radiation, 80 million years, it's the first light that appears. And if you're here this evening, it's because this radiation was homogeneous indeed. There's a bit of a blue and red, a few degrees different, and that's how we've created galaxies and stars and life. So very quickly, I'm making fun of my colleagues. We're talking about a universe. These are the theories and these are the proofs. And the origin. At the beginning, I suggested that the second presentation would be in English to slow things down. Anyway, the stars are made up of gas. And what about the planets? Are they clusters? It's something... The cook has spoilt the broth, I don't know. All the astronomers believe today that planets are a subproduct or a derivative of planets. There are far more planets than there are stars, some think. So this is a question which is beyond science, because in the primitive tribes in Australia, in Eskimo land, every tribe had a myth. What was the part of the role of the myth? Explain the origins of Earth, and people were it was like a founding myth of the tribe. So I started writing a book 1,800 pages. I never had it published because otherwise I could have marketed it as a tranquilizer. So everybody says, oh, it's written in the Bible. If you're a Muslim, the origin of the world is in the Quran, and if you're a Jew, it's in the Bible as well. So there's a French theory, an English theory of the formation of planets. The English would say a star went by, and then the French said it's a nebula that's flattened, and we also had all sorts of other bones of contention. And in 1953, we got the answer, and the English were in the wrong. So if the Earth has come from the sun, then there's practically no hydrogen left. If it's come from a cold environment, you go home tonight, you let the tap run, and you count the hydrogen atoms, and depending on the number, you will see who's right, the English or the French, and tomorrow morning you'll tell me who's right. And then a few years later, the United States of America and the Soviet Union came up with their own theory to say that the bodies, in fact, hit one another, and depending on the side of you're on, you will have a different explanation. So very quickly, the French vision, the English vision, nebula. This is a picture taken a few days ago. We found a disk of matter. It's 1 million years old. We thought that these divisions were made by the planets. Apparently, that in 1 million years, we haven't had time to create a planet. It's an extraordinary result which has just been achieved. So this is a Neptune ring. Comets, no time. Asteroids, no time. The Gerasimenko comet, Wednesday, a probe is going to land, so I shall be here on Tuesday and Friday, and Wednesday I have to go back to Paris. It's going to land on this comet, which in fact is totally different to what we expected. It's very dark indeed. It could have done it 30 years ago. It's a quite extraordinary picture of these comets. These are pieces of matter that have made up the planets. They're the bricks that are left on the building site. These are the bricks that have been used to create planets, and this is where we're going to land. It's not easy because if we land too hard, we're going to be bogged down, and if we slide down the hill, so it's very complicated. Football players, when they're shooting a penalty, don't always manage to put a goal in, but we have to do it. So collisions, this is a wedding, we kiss. This is divorce, so weddings and divorces, which means that we're going to have an accumulation of planets. Not very pleasant, but it doesn't last for very long. And then the script of planet formation, you have nebula, which is flattened by gravity and gravitation. So temperature density increase when we reach 10 million degrees. As thermonuclear fusion, you have energy for 10 billion years. And around you have a nebula that are striking one another, rubbing, and then you need slightly more in the vertical than in the horizontal. So you have a flattening, a ball of gas, and a disk on the periphery. So we have a gas disk, hot, and then as the sun stops the contraction, there is thermonuclear reactions, and then you have grains depending on the distance from the sun. In these grains you have instability, 300 meters, 600 meters, And then there are, as I said, a lot of friction. There are embryos that are created 1,000 kilometers apart, and then when they hit one another, we create planets. So I couldn't create planets. I would break these bodies, and then I got a circular body. I didn't get enough material, and we understood why it didn't work, because we're here thanks to Jupiter. Thank you, Jupiter. Without Jupiter, we wouldn't be here this evening. Jupiter played a very important role. I thought naively that Jupiter was created after the terrestrial planets because it was bigger. Not at all. Far from the sun there is hydrogen and helium, so it swallowed all the gas, and that's why there are no planets between Mars and Jupiter. Mars is tiny, and Earth and Venus are more or less the right size, because Jupiter gave them enough material, slowly, so that it didn't break. And this is very important in terms of formation, but also very quickly, thanks to Jupiter. Look at Jupiter, Saturn, Uranus and Neptune. There are resonance phenomena. You know, when you were 7 years old, I would push my cousin on a swing. If I did it haphazardly, nothing happened, but if I had the right rhythm, there was greater amplitude. My cousin used to scream and my mother would tell me off. I found that very funny. So at 7 years old, you can understand what resonance is all about. So planets are going to start resonating, and this is what it's going to look like. You'll have a massive bombardment, and this bombardment, you can see it on the moon and happened on the Earth as well in 3 million years or 3 billion years ago. This is when life happened. It should have made life disappear, but quite the opposite, because with this bombardment you get material, goes through the Earth crust and allows raw materials to be created from within and from without. So at the end of the day, Jupiter played a very important role in the Sun's formation. 30 seconds, lot of molecules, water, etheric water, and we now can observe stars which are being created. And here you see the systems which are being created. These are tiny solar systems, and this is a very short-lived phenomenon, but we thought was impossible. I was told as a student, star formation is so brief, you'll never see it. Well, today, thanks to the infrared, we can penetrate the system, we can see the babies being born, and we can hear them babbling. So that's how the sun was born. I can show you these results. They go back a few months, so there's a lot of material being ejected and disks around the equator. It's a good idea to be able to then create planets. And then Herschel's satellite, which has looked at the Milky Way on that wavelength, has discovered something extraordinary. These filaments and these stars are created within the filaments, and the stars are two ways of creating them, the light ones and the heavy ones. Like in the life today, there are people who are thin and the ones that are fatter. The fat guys have fun every day, but they don't last very long. The thin ones, they don't party, they're very, very conservative. They're very bored and they go on for ages, and the same thing applies to stars. So what do the huge stars do? They have all sorts of energy. They party, they create atoms and create carbon and oxygen and aluminium and calcium, magnesium. And what's in your body, you have a bit of magnesium, calcium, etc. Everything that's in you, and all these atoms have been created in the stars. So when I'm told and asked by the policeman how old I am, well, I'm 1 billion years old, and the rest is something which is confidential, is none of your business. So this is the Gould, the lighter stars and the heavy stars, the Rosette Nebula. You see how they are created. They're created differently. You've got filaments. Here you have, along these filaments, you've got the detail, the quantity, the number of molecules, the infrared. You see here that there's dissipation of the magnetic field, the fragments which appear here. And here, if you follow the magnetic field, there's a accretion process along the filaments. Here in the Rosette Nebula, you've got the stars that are appearing. You have protostars in blue, the massive hearts or cores which are being created. So you have the lighter ones along the filaments. When you accrete material and when the density becomes critical, fragmentation takes place. Huge stars, the filaments and the cores are created simultaneously. It's a bit more complex, I can't go into the details. And we have to ask ourselves about the phenomenon of life. On 17th December 2013 we had more than 1,000 exoplanets. In 2014 we've gone way beyond that. Have all sorts of sizes and shapes, and you see that the universe is made of hydrogen and helium, and life is made up of oxygen, carbon, nitrogen. So if you want to create life, you go along to the supermarket and buy a bit of all of those and you'll be able to create life. And you have extremophils. This is in fact a water bear. It's happy whether it's cold, hot. In a nuclear power station currently exploding, they're very peaceful and they are indestructible. They take out the water of their cells and they resist. If we had the same technique, we could do a great deal. So life can be found everywhere else. So can we communicate? We don't have time to communicate. And at the end of the day, I'll end on 2 slides, just as a joke in this story which I told you, that our small brain doesn't allow us to understand a lot, and there are lots of mad professors. There's a creator of the universe, the life in the universe is a drawing, is totally stupid. But between these 2 pictures, a man on the moon and a track in Africa, a trail left in Africa 3.9 million years or 2 hours, an imaginary Big Bang on the 1st of January, and today with 31st of December it's only 2 hours, and that's the whole story of humankind. It's extraordinary. We've understood so much in so little time with such a primitive brain. One last slide. So this is summing up our knowledge. This is for ladies. So we do have a heart, and Woody Allen, the day when scientists will discover exactly where the universe is to be found, in the center of the universe, they'll be so disappointed because it's not them. So I'm going to leave it at that, but I find that you could have stopped me before. Thank you.
C'est long, hein. C'est là. Je sais pas si les interprètes ont pu traduire quelque chose. Ce que j'ai remarqué, c'est que sur les blagues, sur la durée, ils rigolaient pas.
Merci infiniment pour...
Well, thank you. I told you he was a bit of a maverick. Okay, we're going to get all your questions, and I would ask the other 2 speakers to join us on the rostrum, and we will resume in about 5 minutes' time, and we will answer your...
Parmi les questions qui vous ont été...
I'm going to make a selection amongst the various questions that have been asked. A little girl, 10 years old, asks you, I suppose, what are these filaments? Can you hear me? Okay, so basically speaking, I can't see anything. I imagine that there's still an audience in the room. So imagine an interstellar environment with matter, atoms and molecules. At certain places it is denser, and at others the density is less. So at denser places you will have more material gathering together. What we noted with these recent observations was that everything gets together in the form of very wide and long filaments, which have nothing to do with filaments of galaxies. It's not exactly the same kind of dimensions. Now, this is an observation, this is not theory. And when you see these filaments, you note that in certain cases these filaments develop, gather mass and material, and reach a certain critical density. When this density is reached, there is a stellar heart created that will form a star. When filaments are more numerous, with a kind of network of filaments, these network might cut itself into pieces, and then a massive star will be created. This is a very complex phenomenon which I didn't have time to develop earlier on. Light stars will bring us warmth for a long time. You need both to exist. On the one hand, matter, and on the other hand, warmth. These filaments are just ways of for matter to gather together. Condensation takes place in the form of stellar hearts, with no creation of fuses that would also be possible in mathematical terms. I have here two questions about life of stars, with more general questions later on for all the other participants. Can you please tell us why the length of life of massive stars is shorter than for other stars? Well, this is very simple, because there is a huge density, pressure and temperature at the heart, at the core of the star. There is a lot of energy being spent, which you cannot go on spending for a long time. Of course, at an astronomical time scale, 5 to 10 billion years. If you have, on the other hand, a star with far less density, temperature and intensity, you can save your energy and last for billions of years. With 1/10 of the mass of the Sun, a star could live for 50 billion years, longer than the life of the universe itself. If you have a car and put petrol in it, if you drive at 400 miles an hour on the highway, you'll probably spend a lot of energy. But if you drive at a not so fast pace, you'll probably last longer. A question maybe to all of our panelists. This is the question. You can see Christopher Nolan's film Interstellar. I don't know whether you've seen it already, dealing with the space-time and the discovery of planets where man could live. Is this only an imagination? Is it really possible? Can we colonize new planets? First of all, as far as the film is concerned, the movie has wonderful technical details, but unfortunately the scenario is very poor. Now, of course, the answer to the question is yes, we could colonize new planets, but not today or tomorrow, certainly not Mars. But if I send you to Mars, you're probably going to boil, which is not very nice. If I send you to Venus, there is a temperature of 400 degrees, and you'll breathe in sulfuric acid. In other words, it's not really hospitable. On the other hand, if you want to go to another star, find another kind of planet, this is not a stupid idea. It can't be contemplated for the time being, because closest possible places are already thousands of light years away from us. But in a very, very far away future, we might find new and faster transportation means, and we could possibly go to another planet. But time will not be felt in the same way. The clock in the spaceship will work differently as the clock on Earth. This is the famous paradox. If you have two twin brothers, one on the Earth and another one sent on voyage in the space, if they come back, they will have a different age. So you could obviously imagine a traveler tomorrow going with a spaceship somewhere to a star. He wouldn't be able to come back. But when Christopher Columbus went to America, the first people who emigrated left Europe 1 century later, and they didn't come back to Europe afterwards. We could imagine that one day people would leave the Earth without even coming back. We could all think of people we would like to send to the outer space. This could be contemplated, of course, and we could therefore think about the future of the history of mankind. Maybe another question. There is a question that is very general here with the following wording. You are the living proof that matter is inhabited with spirit. What do you think about that? This capacity, this ability of matter to think about itself. There is no spirit without matter. Some people think that there is a soul, you could think about it, but there is no proof, no experience, no evidence of that. The spirit is not something proper to man. Animals also recognize itself, they communicate with each other. If you put a blue spot on an elephant, they would be recognized by other elephants. And the elephant in the mirror would try to get this blue spot away because he would recognize himself as having a spot. All living beings have a kind of spirit. Take human beings. We have a skin. We need energy from the outside to live and to escape predators. Well, same thing for a cell. A cell would try to get away from something that is toxic for it, and they also have a membrane to delimit itself from the outside world. I was able to swim in the ocean with a dolphin, and that was a wonderful animal that talked to me with sounds. Of course, I was not able to speak in the same language, but obviously there was a spirit behind or in that animal. All human beings and living beings have a form of spirit. But there is no spirit without matter, contrary to what some people might lead you to think. The spirit is the result of matter. But other people may have different opinions about this. Do you want to say something about this topic? But also have a question to Jerry in relation to this evening's conference. You are indeed going to talk about the influence of the sun on the climate on Earth. The discovery of extrasolar planets and the ability to have an idea of what their climate might be might help us to know better what's happening on the Earth and within the solar system and what the way our climate might develop. What can you tell us about the link between the outside world and the climate on Earth?
Well, it's I think there's a lot of scientists that actually try to study planetary atmospheres, and anything you can learn about the physical system, no matter where it is, gives us insight into what's happening on Earth. And I think that's one of the reasons scientists like to study atmospheres of other planets, because when you're in a totally different environment and you still see some things that resemble Earth in some ways, but they're fundamentally different, as Andre was really highlighting tonight, it gives you different kinds of almost laboratory experiments, because you can try to look at, say, the atmosphere of Mars or the atmosphere of Mercury and say, okay, well, this is what their Venus is another one that's very instructive because it's a very intense greenhouse gas environment that's containing a lot of heat on Venus, makes it very hot. So I think anything you can learn about any of these other planets gives us insight into what's going on Earth ultimately.
Alors, peut-être un petit...
Maybe one word from Art MacDonald. You've indicated that for many, many years we were able to discover or to calculate the temperature within the sun, at the center of the sun. For those who will not be able to attend your conference tomorrow, can you say a few words about what we know about the temperature at the core of the sun, which we know thanks to these particles that come to the Earth?
Yes, the measurements that have been made by our experiments and others of particles called neutrinos, which are created in the nuclear reactions that power the sun. As has been stated, we know that the power that is generated to power the sun comes from nuclear reactions. And in the process of these reactions taking place, particles that are outside of our normal experience, because they interact with things so very weakly, are able to carry information from the core of the sun through the very dense material in the sun and through the Earth, in fact, and interact with our detectors. These neutrinos are, along with electrons and quarks, the three particles that we don't know how to subdivide any further. They are the basic building blocks, as far as we know, in subatomic physics these days. And yet they are not charged, so they don't feel the electromagnetic force. They don't feel the strong interactions, and so they only feel them, the most weak interaction that there is of the set of forces of nature. And so they can go through, well, they only stop basically if they hit the nucleus of an atom or one of the electrons going around it head on. And so they can go through the amount of lead that light traverses in a year and only have a 50% chance of stopping. Now that's great when it comes to trying to study the sun, but it's very difficult when you're trying to build a detector in order to observe them, because they interact so very seldom. And so we built a detector which is about the size of a 10-story building. We built it 2 kilometers underground in a active nickel mine. They're taking about 5,000 tons of ore a day out of the same shaft that we used to go up and down and build the detector. We built it in an ultra-clean state because we look for faint bursts of light. In fact, about once an hour in 1,000 tons of a material called heavy water, we would see a burst of light that corresponds to a neutrino. On the other hand, if you're very careful, if you restrict the radioactivity such that there is no radioactivity from the cosmic rays that bombard the Earth by going 2 kilometers underground and using the rock to get rid of that background, and if you're very careful in building your detector to build it such that there's no local dust on it, and you select your materials very carefully, you can actually observe this 1 neutrino per hour and determine whether or not the theories of how the sun burns are accurate. And we were able to determine that in fact they are accurate to within less than 10% comparison between the theories and our measurements. And we, in the same time, were able to make measurements of the properties of neutrinos themselves, because we observed that they change from one of the 3 types that there exist to the type that's produced in the core of the sun. We observed them changing into the other types and reaching the Earth, which had confused all of the experiments up to the point that we performed ours. What's fabulous about observing that we understand how the sun is burning in great detail is the fact that our sun is just the start of a series of nuclear reactions, as was mentioned earlier, in which all of the elements of matter of which we are made are created. You start with hydrogen burning to produce helium. Gradually, in more massive stars than the sun, you end up with the helium burning to produce carbon. Carbon then burns to produce neon and magnesium, and eventually you end up with all the heavy elements being produced in supernova. When the energy generation in the core of the sun or of any star is exhausted because you've burned it all by nuclear reactions, you get an explosion, an implosion really, and that is where the remainder of the elements are produced. And so by studying in detail our sun, we're able to study the start of the set of nuclear reactions that really are responsible for producing all of the elements on Earth. And that is a major accomplishment that has occurred over the last 20 to 30 years. And it's pretty remarkable to be able to understand your origins with that sort of accuracy. So that's what I'm going to talk about tomorrow, how we were able to do those measurements, but also how it is the sun burns and what relationship that is to how all of the elements of which we are made are produced. So, thank you.
Merci beaucoup. Je crois.
Thank you very much. I think we are going to call it a day because it's already 8:15. Thank you very, very much indeed, André Braig, but also Thierry and Art MacDonald. I wish you a good evening, and there is also the show at 8:30 now.